Hello, we are from the Novel Mobile Robots Lab at UIUC, and we're here to present a latched spring actuated robot for jumping and perching.
Squirrels are iconic animals on UIUC campus. Their agile locomotion capabilities are particularly inspiring. As robotists, we are very interested and we determined to create a tree jumping and climbing robot. In this work, we focus on the tree jumping instead of climbing, which we believe is the first step towards agile locomotion between distant angle surfaces.
A natural solution would be to scale down existing quadrupeds. However, these are direct drive, which means that the jump height is limited by the length of the leg and the motor power, and which both of these will scale down as the robot scales down. So our solution is to use a latched parallel elastic mechanism that stores energy into a spring, and so this means that the jump height is only limited by how much energy we can pack into a spring.
Here's the mechanical overview of this squirrel-like robot. We have two front legs, which are driven by 5 servos, and we have a single back leg that is driven by 2 twisted string actuators. In addition, we have a roll cage to help the robot self-right when it's flipped over. And we have a compliant tail to help the robot achieve this goal even if it is on an uneven surface.
So here is our 2-degree freedom rear leg. There are brushless motors that spin a string, and as it turns, it contracts like a muscle that pulls on the linkage and positions the foot. So in the unlatched mode, we can precisely position the foot without compressing the spring. However, in the other mode, when we use the latch, we can have the carbon fiber springs compress and then automatically release when it reaches this endpoint. When the linkage moves back, it can reset the latch like that if it goes all the way back. If it does not move all the way back, we can stay in unlatched operation to keep control of the foot. We design a spring such that the motor can apply a near constant torque to wind up the spring along the entire stroke, and we found that this particular ratio of the link lengths is great at making this constant torque such that the motor can always be operating efficiently.
Here's the video of the tree jumping experiment. In this experiment, we used the latched elastic jumping mode to achieve the highest jumping energy. In the early phase, these springs are compressed, and then all the energy are released all of a sudden. At the end, the robot perched on the tree using the fish hooks grippers, and the center of gravity is able to rise roughly 1 body length.
Let's take a look at what's going on inside. So we have at the top 2 graphs, plotted in the light colors, the motor input, and in the dark colors, the spring. So the difference between the 2 positions represents the energy storage, how much the spring is compressed. So during the first 120 milliseconds, it winds up this spring, and then it latches release, propelling the robot.
Here's the experiment data that shows the jump energy versus jump time of the 3 jumping modes. In the red region, shows the parallel elastic actuation mode, which takes longer time since it requires the springs to preload. However, we're able to achieve a higher jumping energy using this mode.
On the right, we can see some other behaviors that the squirrel can do, such as righting itself from its uneven terrain using the tail. But the main takeaway from this project is that our latches can enable switching between a parallel elastic mode, where it stores energy in the spring, and also a continuous control mode, where we can remain controlling the foot position. Also, the brushless DC and the twisted string actuator provide a low weight but high mechanical advantage transmission that are good at launching things. Thank you, and see us at the poster.